Hey there, Venkat. Welcome to your ultimate science explainer. I am absolutely pumped to step in as your personal tutor today. I know you've got that big 7th standard science exam coming up. And listen, my only goal today is to make sure you walk into that classroom feeling 100% confident. Today, we are going to perfectly memorize the ins and outs of heat energy. I've custom built this explainer just for you, breaking down all that textbook stuff into super clear, bite-sized pieces. So grab your notebook, get comfy, and let's master this topic together. So let's kick things off with a classic mystery right out of your textbook. Picture this. You're stirring some hot tea or maybe hot milk with a stainless steel spoon, and you just leave it sitting in the cup for a minute. When you go to touch the handle again, it's gotten warm. Now, why exactly does that handle become warm, Venkat? It wasn't even touching the liquid. Well, this little mystery is the absolute perfect introduction to the invisible energy we are investigating today. All right, here is our game plan for today's masterclass. Number 1, the flow of heat energy. Number 2, measuring heat and temperature. Number 3, modes of heat transfer. 4, conduction and vibrating molecules. 5, conductors versus insulators. And finally, number 6, cracking glass and trapped air. Okay, section 1, the flow of heat energy. Let's dive right in. All right, Venkat, I want you to draw a giant star next to this in your notes because it is an absolute exam must-know. What exactly is heat energy? Well, it's a certain type of energy that flows between two bodies when there is a difference in temperature. And here is the absolutely crucial part, right at the bottom. It always, literally always, flows from the hotter region to the colder region, never the other way around. When this energy flows into a body, it warms it up. When it flows out, it cools it down. And if you just leave them alone, this flow continues until the temperatures of both bodies become exactly the same. They balance out. Let's lock this concept in with a quick virtual lab. Imagine we take 2 glasses and fill them about 3/4 full of cold water. Then we take a coin that's been sitting in boiling water, so it is really, really hot, and we drop it into just one of those glasses. We wait maybe 2 minutes. Now, if you dip your finger into the glass without the coin, the water is still cold, right? But if you dip your finger into the glass with a hot coin, the water is suddenly warmer. This brilliantly proves our definition. Heat energy transferred directly from the hot body, our coin, to the cold body, the water. Moving right along to section 2, measuring heat and temperature. Okay, red alert here, Venkat. I'm setting up a warning sign because examiners absolutely love to set a trap with these 2 words. What's so interesting about this concept is how it separates 2 things we honestly mix up all the time in everyday life. Let's get this right so you don't get tricked on a true or false question. Temperature is actually not energy itself. It's just a measurement. It's a number that helps us calculate the amount of heat energy a substance contains. Heat energy, on the other hand, is the actual physical energy flowing between the hot and cold bodies. So they're definitely related, but they are absolutely not the same thing. Keep that straight. And hey, speaking of measurement, just like we measure length in centimeters or meters, we have to measure heat energy. The SI system, the International Standard System of Units, measures heat energy in joules. Thank God, I want this giant J completely seared into your memory for the test. Whenever that exam asks for the unit of heat energy, you confidently write down joules. All right, section 3, modes of heat transfer. So we know heat flows, right? But exactly how does it travel? Well, there are 3 scientific modes, or methods, by which heat is transferred from one place to another. They are conduction, convection, and radiation. While it's definitely important to know all 3 names for your exam, for today's masterclass, and specifically for understanding how solid objects like that spoon heat up, we are going to put all of our focus on conduction. Which brings us to section 4, conduction and vibrating molecules. For this one, Venkat, I want you to imagine shrinking down to a microscopic level. We're going to look inside a solid object to see exactly how this magic happens. So here is your highly precise definition for conduction, perfect for your flashcards. It's the primary mode of heat transfer in solids. For it to happen, 2 bodies must be in actual physical contact, or it can happen from one end of a single body to the other. Now, matter is made of tiny particles called molecules, and in a solid, they are tightly packed together. They can't just move around freely, but they do vibrate around a fixed point. So conduction is the transfer of heat by actual physical contact, where these tightly packed particles vibrate and transfer energy to their neighbors, without ever leaving their original positions. Think of it like a microscopic relay race. When you heat one end of a solid rod, the nuclei closest to the heat start vibrating faster and faster. They physically bump into their slower-moving neighbors, basically passing the energy baton down the line. But here is the secret weapon of metals, Venkat. Metals have some loosely held electrons that can actually move about freely. When heated, these free electrons zoom around, bumping into other electrons and nuclei, passing that energy incredibly rapidly. Nonmetals? Well, they lack these loose electrons, which is exactly why they don't conduct heat very well.
Let's actually prove that metals do this better than anything else, but also that not all metals are created equal. We're going to do another virtual lab, the metal race. We take rods of equal length and diameter made of aluminum, iron, and copper. We use some wax to glue small metal balls at equal distances along each rod. Then we stick all 3 rods into a central burner and light the flame. The heat is going to conduct down the rods, melting the wax, and those metal balls will start dropping off. It's a literal race to see which metal conducts the heat the fastest.
And here are the podium finishes. I want you to memorize this exact ranking for your exam, okay? First place goes to copper. Its balls drop the fastest, meaning it has the absolute highest rate of conduction. Second place goes to aluminum. And coming in third place, the slowest of the 3, is iron. So while all metals are good at this little relay race, copper is the undisputed champion here. Moving on to section 5, conductors versus insulators. Now that we totally understand the relay race, let's categorize some everyday materials based on how well they let that race happen. Conductors are materials that allow heat to pass through them easily. As we just learned, all metals are good conductors, like copper and aluminum. Insulators, on the other hand, are the exact opposite. They are materials that do not allow much heat to pass through. Your textbook gives some great examples you should definitely list out: wood, straw, clay, rubber, glass, and bakelite, which is a kind of plastic. And amazingly, water and air are also really good insulators. Let's test this out with the hot cup challenge. Imagine carefully pouring very hot water into cups made of glass, plastic, ceramic, stainless steel, and copper. The water inside is the exact same temperature in all of them, right? But if you lightly touch the outside of each cup, the stainless steel and copper cups will be really hot, like almost burning. The glass, plastic, and ceramic cups will just feel warm and completely bearable to touch. This brilliantly illustrates that even with the same temperature inside, the rate of heat transfer through conductors like steel is extremely high, while insulators basically block that heat from reaching your hand. Finally, section 6, cracking glass and trapped air. All right, this is where we apply everything we've learned to those tricky why questions teachers absolutely love to put at the end of tests. First test question: why does thick glass crack when you pour very hot liquid like tea into it? Well, Venkat, the answer is uneven expansion. Because glass is an insulator, it does not conduct heat well. So when the hot liquid hits the inner surface of the cup, that inner glass gets hot and actually physically expands. But the heat doesn't travel through to the outer surface quickly at all. The outer surface remains cold and unexpanded. This uneven heating literally pulled the glass apart, causing it to crack. Boom! Now you know exactly how to answer that. And here is another amazing piece of natural science trivia. We mentioned earlier that air is an insulator, right? Well, animals have been using this physics trick for millions of years. Materials like wool, fur, and bird feathers aren't just magically warm on their own. They become incredible insulators specifically by trapping tiny pockets of air between their fibers. That trapped air stops the animal's body heat from conducting outwards into the cold. It's just brilliant. Which actually leads me to this provocative thought question for you, Venkat. If you ever had to build a survival shelter out in the freezing snow, how could you use that trapped air trick to stay warm? Think about it. Fluffing up dry leaves, making layers of branches, basically creating little pockets of air between you and the cold ground. By understanding that air is an insulator that blocks conduction, you aren't just passing a science test, you're learning how the physical world actually operates. And just like that, we're wrapping up our heat energy masterclass. You now know the difference between heat and temperature, the microscopic relay race of conduction, and the awesome real-world power of insulators. You've totally got this, Venkat. I want you to review these notes, and hey, grab your classmates and friends and have them listen to this explainer too. Science is always better when we learn it and ace the test together. Good luck on the exam. You are going to do absolutely incredibly.